Hello everyone. Here I want to show only some basic details about my work called double-step spin transition in binuclear iron-iron helicates with encapsulated anion by NMR spectroscopy. The chemical and structural formula of the studied compound is presented on the slide. As you can see, in addition to the ligands, it contains two iron atoms and encapsulated bromine or chlorine anion or ion inside. Yes. Usually for pure high-spin state iron-iron in NMR spectra, we observe linear dependence of chemical shift from inverse temperature as a result of the QE behavior. If spin transition presents, this dependence is averaged with over two spin forms of iron, low spin that is diamagnetic and high spin that is paramagnetic. Yeah. On the slide depicted the dependence of chemical shift from inverse temperature for our complexes, and this observation is very interesting. First of all, it's interesting because we have the temperature range where we are not observing some of signals in the range from 230 Kelvin to 200 Kelvin. And at the same time, there are two signals that are observed in the entire temperature range. These are protons number 7 and 9. And as we can see from the structure, these protons are equidistant from two iron atoms, and because of that, their chemical shifts are independent on exchange between these two forms, also depicted on this slide. This exchange is possible when the double-step spin transition is presented, because in our system we have high spin form and also high spin low spin form, and the presence of this form can also be proved from chemical shift dependence for proton 9 and 7. And if you have some question, I will glad to see you on poster session.
Thank you. Thank you very much. The next possible speaker, Aleksandra Andrzejowska.
Yes.
Рассказал. Ой.
Yes.
Yes, thank you. My name is Aleksandra Andrzejowska, and I am an ungraduated student of Professor Hubert Harańczyk from Jagiellonian University, and I am going to present you my research of molecular dynamics of bound water in Umbilicaria Antarctica Tari by proton nuclear magnetic resonance. Umbilicaria Antarctica is an Antarctic lichen. It has outstanding ability to stop its life processes and restart them when the outside conditions get better. It can carry out photosynthesis in temperatures as low as minus 15 degrees centigrade, even covered by snow. Last but not least, it has highly antioxidative capabilities. To perform this experiment, we used desiccators with different relative humidities and observed mass growth. Then one for humidity up to 32 and two for higher humidity, exponential functions were fitted. At humidity over 88%, total hydration levels increased more than twofold. Total saturation hydration levels as a function of relative air humidity was taken to construct the sorption isotherm. For multi-layer sorption processes, two theoretical models are usually considered, PET and GAP. Both models are described by these parameters, delta M over M0, which is the mass of water saturating primary binding sites, 1 over B1, which is the number of unoccupied primary water binding sites at H = 1, and H as humidity. A gap model is simply expanded model bed by adding B parameters, marked red. Parameter B describes the ratio of binding sites covered by N water molecules, expressed in units of binding sites covered by N-1 molecules at maximum humidity. And now let us look at the results. Free water fraction were observed by hydration kinetics, very tightly bound, not removable even at 0% relative air humidity. This fraction has a very low mobility and it's tightly bound to the solid state matrix of the talus. In the picture, signified with the thickest lines. Tightly bound water in the picture, this fraction is illustrated by thinner solid lines, and loosely bound water, this is a fraction with the highly mobile, and in the picture illustrated by thin dashes lines. Now, I'd like to present you my final value of parameters and what they mean to us. B value significantly lower than 1 means that the water in the organism is forming clusters. Value of 1 over B1 near 0 means that the talus of Umbilicaria antarctica is highly hydrophilic. Now, 1 solid state and 2 water fractions were observed by NMR spectra. Solid state is fitted well with Gaussian function. Tightly bound water and loosely bound water were fitted with Lorentzian functions. For tightly bound and loosely bound water, the peak position of the Lorentzian lines are different, which may be attributed to the difference in chemical shifts. In the time domain, we observe 1 Gaussian component for solid state and 1 exponential component for low hydration levels representing liquid state. And for higher hydration levels, a second exponential component can be fitted. This signifies the appearance of loosely bound water fraction. At the same time, hydration level first component relaxation time start to decrease. The total area under both Lorentzian peaks over the total area under Gaussian peaks is well described by a rational function. The surplus in mobile signal may be caused by a presence of solid water soluble fraction of talus, which dissolves with the increased hydration level of the sample. The saturation concentration of the soluble water fraction resembles that for those sugar, sucrose, xylose, and galactose. To sum up, free water fraction were observed by hydration kinetics, very tightly bound, and loosely bound, and only 2 by NMR spectra. Drastic increase in total hydration level for air humidity over 88%, suggesting restart of life processes in this organism. Umbilicaria antarctica has a highly hydrophilic talus. Solid water soluble fraction was detected with value resembling those of some sugar. Peak position of the Lorentzian lines are different due to chemical shifts. And this is my reference, and thank you very much for your attention, and I will happy to answer any question in this poster session.
Thank you, Aleksandra, very much. And the next possible speaker, Валерий Безродный. Валерий Безродный, ау. No. Then Dmitry Blakhin. They don't want. Agata Bogdał. Agata Bogdał.
Владимир,
Да.
за нее Карол Кубат.
Что?
Извините, Карол Кубат, соавтор у нее.
Hello.
I was prompted that
Карол, please.
somebody
Yes.
will.
Welcome. I can show you the
Yes.
poster of the
You
Agata.
instead of Agata. Yes.
Yes.
Yeah. Please. 5 minutes.
Yes. So to quickly sum up her work, because she is in the hospital because she is making a new life in this world. So as Mrs. Aleksandra was saying, as she is in our group, we try to classify the residual bound water fractions in a lot of compounds, and Mrs. Agata Bogdał is working on the phospholipids and liposomes that are firstly they are dry freezed or lyophilizates, and after that they are put in the excitators with the relative humidity of the 100%. So we can rehydrate them to check their hydration kinetics, and with the exponential function that describe the time of the hydration. The faster time means that this part of the water have the higher energy bonding to the surface of the molecules of the samples, and the lower, actually bigger time of the hydration have the lower energy and is more loosely bound water. At the NMR spectra, we distinguished two Lorentzian peaks and one Gaussian function was fitted. For the DOPC liposomes and DPPC liposomes. And the difference is that in the DPPC, we observe only maximal hydration at the level of the 25%, and the Gaussian peak is very broad, around 80 on 90 kilohertz. So the structure is very, very, very stiff. But the water that is binding is very bound water, because the half width of the peak for the Lorentzian functions are around 80 or even around 2000 hertz for the Lorentzian peaks, so they are quite broad, and this means that the relaxation time is quite short for the water that is bound to the surface of the liposomes. But for DOPC, we can observe only one sum of the, not for DPPC, we can observe only one sum of the water that is bound to the surface, and this peak is just some of the half width of the over 2000 hertz, so it's much broader than in the correlation to the DOPC, which is more mobile, and it's in a different state, of course, because DPPC is in the gel state at the room temperature, but the DOPC is in the liquid crystal form. So there we can see maybe differences in there, not simply because of the bounding water. So thank you for your attention, and I think I could answer some question in the poster section, but I will be not so in the topic as the presenting author.
Thank you very much, Karol. And the next person which I like to invite, Anna Butyugina.
So, good
Thank
evening.
you,
Good
Anna
evening.
Butyugina. Please, 5 minutes.
Yes. So my name is Anna Butyugina, and my work is a computer simulation of ionic liquid 1,3-dimethyl imidazolium tetrafluoroborate in smectic-A phase. It was decided to start modeling the initial system by modeling ionic liquid in the freely distributed program GMO. To calculate the charge in the system, a simulation was carried out by the method of quantum chemistry in Gaussian 16. Two models were used, the Hansel-Fock method with standard basis function 631 ++ g, and couple clusters method with basis function CCPVDZ. Calculation showed that in the first system, the total charge on the ion is minus 0.9, and in the system calculated using the basis function CCPVDZ, it is minus 0.88. Then, using the Aleksandra program, they simulated 330 ion pairs. In Selivanov, so it follows from the graph that the numerical value of the radial distribution function at large distance increases, and a system of a charge distribution of 631 ++ g, this occurs more slowly than in CCPVDZ. That is, the alkyl change diverges faster in the system with the CCPVDZ basis function. The radial distribution function of the interaction of the hydrogens of the imidazole ring with the fluorine atoms of the ion was also considered. In both systems, the form of the David's dependence is the same and corresponds to the theory. The difference are only in the numerical values of function. It can be seen that during the simulation, the radial function practically did not change into system, so the simulation continues at the moment. The estimated diffusion coefficients was also determined in a system with a charge distribution of 631 ++ g. It's of order 1 multiplied by 10 to minus 24, while in our system it has a higher order. Thus, the system with basis function CCPVDZ is more correct. Thank you for your attention. I am glad to answer in the poster session.
Thank you. Thank you, Anna, very much. Thank you. And the next person, Maria Dmitrienko. Are you here? Maria Dmitrienko. No. Next, Emil Fatulayev. Emil Fatulayev. No answer. Like in Tom Sawyer. Tom, no answer. Next invitation, Albina Gafarova.
I'm here. Good evening.
Please, 5 minutes.
I will speak about APR study and DFT-assisted.
Excuse me, have you a presentation? Short presentation for
Yes.
Twice. It's better to
Mhm.
accept. Oh, yes, thank you.
I will speak about APR study and DFT-assisted identification of radicals in gamma-irradiated calcium gluconate. Calcium gluconate is widely used in the chemical and food industries. It's used as a drug for the treatment of disorders associated with a lack of calcium in the body. Also, interest in the study of this compound is high in connection with the development of a mechanically activated, modified, non-dispersed amorphous form of calcium gluconate. The treatment efficiency of which is much higher. Given the high importance of calcium gluconate for industrial and medical applications, it's surprising that its structure has remained unexplored for a long time. This may be because the traditional method of slowly cooling and aqueous solution produced very fine needles with correspondingly weak X-ray diffraction. Thicker crystals providing good data quality on a laboratory diffractometer were obtained by Bugres et al. However, mechanical activation is often accompanied by amorphization, which makes it impossible to use diffraction methods. In this regard, it becomes necessary to use alternative research methods. In particular, this work considers the possibility of using the APR method to determine the conformation of calcium gluconate. Since the original calcium gluconate does not have an APR signal, to obtain information about the system, it's possible to introduce artificial defects into it. For this, we used an ionizing radiation in our work. Earlier, we showed the possibility of determining the conformation structure of gluconic acid salt by creating paramagnetic centers in them by irradiation with gamma quanta. Using a different radiation dose and analyzing APR spectroscopy in the X and Q band, it turned out to be possible to decompose hyperfine interaction with the structure of calcium gluconate. However, in this case, one has to make simplifying assumptions. For example, about the isotropy of the factors and hyperfine interaction parameters. In this respect, the method for calculating the parameters of the APR spectrum using quantum chemical methods is more attractive, which was the purpose of this work. Using the Bugres X-ray diffraction data, we built a model of the calcium gluconate molecule in the Avogadro program. This program was used to generate input files for the ORCA quantum chemical program. An internal coordinate system was used, which is convenient for setting the optimization condition. Because it is assumed that irradiation with gamma quanta leads to the rupture of the CH bond, hydrogen atoms in the structure of the calcium gluconate molecule bound directly to the carbon atom were successfully removed, for each case a quantum chemical calculation was performed. The parameters of hyperfine interaction and the factors obtained as the results of the quantum chemical calculation were used to decompose the experimental APR spectra using the EasySpin software. The results of the composition of the APR spectrum is in X and Q band of the calcium gluconate samples irradiated with dose 1000 gray is shown in picture. In this graph, black point is experimental spectra and red line is a model spectrum. Thus, the results of X-ray diffraction studies of single crystal of calcium gluconate made it possible to carry out a quantum chemical calculation by the DFT method of possible radicals created by the method of irradiation with gamma quantum. This made is possible to correctly describe the observed APR spectra of calcium gluconate in X and Q bands with one set of anisotropic parameters, hyperfine interaction, and J factors. In addition, the calculated value of the hyperfine splitting of the radical at the fourth carbon atoms turned out to be much higher than those observed by us experimentally. Thus, this confirms our earlier conclusion about the absence of a radical on the fourth atoms. The touchstone angle obtained from the APR data are consistent with the X-ray diffraction data reported in a recent paper by Bugles. Thank you for attention.
Thank you, Albina. Thank you very much. And the next speaker may be Irina Golubeva. Irina Golubeva. Oh, no answer. Then I invite Sofia Mikhtanuk. Sofia Mikhtanuk. Also no answer. And the
Sophia
last,
here.
yes? Oh,
Sophia here, but no answer.
Sofia Mikhtanuk. I don't see. No. The last person, Alexander Selivanov.
I'm here.
Oh. Please.
Okay, 1 second. I will share my screen. So you can see the presentation, yes?
Yes. Short presentation during 5 minutes.
Okay. Good afternoon to you all. My name is Alexander Selivanov, and I'm a third-year student of Faculty of Physics of the St. Petersburg State University. Firstly, I would like to thank the organizers of this conference for giving me the opportunity to tell you about our investigation. Today, we will discuss optimization of parameters for molecular dynamics modeling of ionic liquid butyl-methyl-midazolam thiocyanate. On this slide, I would like to outline my presentation. Firstly, I will tell you about ionic liquids and review our investigated molecule. Then we will discuss parameters of our calculation, and then we will start discussing density of the box, and the main characteristics is mean square displacement. So let's start. Ionic liquids are room temperature molten salts. They have several advantages which make it possible to use them in new current sources. The purpose of this study is investigating the ionic liquid butyl-methyl-midazolam thiocyanate. This ionic liquid was selected because experiments were provided to determine the physicochemical properties. So in figure 1, we can see cation butyl-methyl-midazolam, and in figure 2, we can see anion thiocyanate. We decided to optimize our system with Gaussian software package. We made 3 different systems. In system 1, we have optimized charges for each molecule. In system 2, we reduced molecule charges by 0.1. And in system 3, we reduced them by 0.2. In figure 3, we can see the ionic liquid after 10 nanosecond simulation in NLT ensemble. Let's move on. At the center of this slide, you can see parameters of our calculation. I want to notice that first 10 picoseconds were calculated in NPT ensemble to equilibrate our system. Then then 10 nanoseconds were simulated in NT ensemble. So then one of the parameters which can prove that our calculation were provided correctly is the density of the box. In figure 4, you can see distribution of density for each system over the simulation cell. As we can see, the deviation of the third system is the smallest deviation from the mean. And at the top of the slide, at the top of the slide, you can see average densities of each system. The main characteristics is main square displacement, which we can see in figure 5 for each molecule in each system. From these characteristic using Einstein equality, Formula 1, we can obtain diffusion coefficients D for each molecule. So in table 1, you can see every coefficient which we have obtained. In fifth column, there are diffusion coefficients which were obtained by NMR diffumetry experiment at temperature 348 kelvins. As we can see, the coefficients for system 3 is close to the real one, but there is difference between them. So in subsequent work, we will investigate dependence of diffusion coefficients from temperature. Thank you for your attention.
Thank you. And the list of